In this video, we are going to discuss about time domain specifications of control system. Why we will use this time domain specifications means the desired performance characteristics of control systems are specified by using this time domain specifications. What are the desired characteristics we want that can be specified by this time domain specifications. So, what are these time domain specifications we need to have means here we are having so many time domain specifications like this. One is delay time represented with TD and rise time represented with TR and peak time represented with TP and peak overshoot or maximum overshoot represented with MP, and here I am having a settling time TS. So, this settling time is always represented with TS, and I will discuss one by one here. In the next class, we will derive expressions for each and every time domain specification. Now, I will give definitions. So, you just take this as a reference waveform to discuss about all these time domain specifications. Coming to delay time, this is the time taken for the response, this is the response diagram, this is the response of a control system. By this response, we can define each and every time domain specifications. So, here C of t is the response. You can see in all control systems we are going to consider C of t as your time response of the system. So, if you observe this time response, so here I mentioned TD. So, TD is the delay time is nothing but the time taken for the response to reach 50% of its final value. So, for example, if the final value is 1, always we will take this as final value, and this delay time is the time taken for the response to reach 50% of its final value from the very first time is called as delay time. You can observe TD rises from very first value to 50% of its final value. So, here TD is the delay time is nothing but time taken for the response to reach 50% of its final value from the very first time. So, coming to rise time. So, this is indicated with rise time. If this is 50%, this is treated as 100%. So, always rise time is the time taken for the response to reach 0 to 100% of its final value from the very first time. So, this measurement, or that means 0 to 100% is for underdamped system. If the control system is underdamped system, whatever the system response we are considering is a underdamped system, then rise time is calculated from the time taken to rise from 0 to 100% of its initial value. If that is a overdamped system, then we will take the time taken from the rise time taken from the time taken from for the response to reach 10% to 100%. I am writing here. So, here if that is 0 to 100%, so if you are measuring from 0 to 100%, that is for underdamped system. If you are measuring TR from 0 to 100%, then we can say that is for underdamped system. If you are measuring 10% to 100% or 10% to 90%, so then that is for overdamped system. The time taken for the response, if you are given with a overdamped system, so this is underdamped system and this is overdamped system. So, if you are given with overdamped system and if you are asked to calculate what is the rise time, then you need to consider the time taken for the response to reach 10% of its value to 90% of its initial value. So, coming to critically damped system, so the time taken for the response to rise from 5% to 95% of its initial value. So, then that is called as rise time in case of critically damped system. So, this is very important when you are solving problems. In the problem, if they given under damping, then you need to consider your rise time from 0 to 100%. If they given over damped system, then you need to consider your rise time from 10% to 90%. If you are given with critically damped system, then you need to consider your rise time as the time taken for the response to rise from 5% to 95% of its initial value. So, like this we need to consider the rise time. Coming to peak time, here you can see peak time. So, the time taken for the response to reach its peak value. If you see, this is the peak value. So, the time taken for the response to reach its peak value is called as peak time. And coming to peak overshoot, maximum overshoot or peak overshoot indicated with MP. Peak overshoot is nothing but, so it's the ratio of the time taken from final value to final value, maximum value to final value to final value. That means I will give you here, if you consider the peak value or maximum value as C of Tp. So, this is the maximum value. So, this is C of Tp. Final value may be, final value of response may be C of infinity. So, I am saying maximum overshoot or peak overshoot MP is equivalent to the ratio of time taken from maximum value to final value to the final value. So, the time taken from maximum value to final value means, so you need to consider like this, C of Tp minus C of infinity divided by C of infinity. The time taken from maximum value to final value this nothing but maximum overshoot or peak overshoot. So, now finally we are having settling time. So, TS is nothing but the time taken for the response to reach and stay in a specific error. So, here the allowable error may be 2% or 5%. So, sometimes you need to consider 2%, sometimes you need to consider 5%. The allowable error may be 2% or 5%. So, settling time means it's the time taken by the response to go and settle in a specified value in the error. So, here the allowable error or allowable tolerance of that error is 2% or 5%. These are time domain specifications of a control system. From next class onwards, we will derive the equations for each and every time, that means for delay time, rise time and peak time, and for settling time we will analyze these from the next class onwards.